Hello again, welcome to Physical Chemistry. Today we're going to look at infrared. So we were looking at the electromagnetic spectrum last time, and infrared is the lowest energy sort of electromagnetic radiation that interacts with chemicals. So let's take a simple molecule, let's take an atom to start with. So this would be an atom of oxygen. It's red. Let's put it a bit closer to you. So this red atom of oxygen, it could rotate, but we can't tell if it's rotating because the orbitals in there can just reorganize themselves, and so we can't tell anything about this atom, or it can't absorb any energy from our light apart from to move around a little bit faster. If we go up to what can we have? Carbon monoxide, which would be this molecule here. Black is carbon, red is oxygen in this particular modeling kit. If we take this molecule, we can see bending is not really likely because it doesn't really make a lot of difference to this molecule, but it could rotate. We can see it rotating, and it could also vibrate in this direction. So maybe we should think about both of those things. If we go up to the next possibility, which is this one, carbon dioxide, if this molecule bends, it is definitely different. Whereas if the carbon monoxide bends, it's still got a carbon and an oxygen, and the electrons, why should they bend? But if we have something like this, it has a possibility, whoops, it's difficult to keep my fingers out of the way, it has the possibility to bend, and we can see that that's definitely different than it was before, and we can imagine it bending in this direction, or indeed in the other direction towards you and away from you, but that those will be exactly the same. If we take another molecule like this is dichloromethane, so these two are chlorines and these two are hydrogens. And we can see that this molecule can rotate, but it can rotate in two different directions. This direction where the two hydrogens stay on the same side, and this direction where they don't, where they change sides. We can also both stretch the bonds in different ways. We can also bend them. These ones don't bend, so I can't do that. But these ones, they can bend, or these ones can bend in this direction. So we introduce a little bit of geometry very simply. Let us have a think about how those might react when we activate them. So if we take what you had in physics, if we take a normal spring, so let me try to draw that because I weirdly don't have one right here. So if we have a spring, hang on, I'll go and get one. So I'm back. This is a spring. Oops, have it a bit closer. This spring can stretch and oscillate, and as you had in your physics, the length of a spring is dependent on Hooke's law. So the length, so if we put what do we want? If we want force and distance, and we start at 0 stretch, we would get a squared shape. That's my eraser. And if we move our distance away from, so that would be starting at the equilibrium position, if we move it to actual length, and we consider it as a spring that can both stretch and compress, we would get a shifted quadratic shape curve. If we take that and add some energy levels in there, because energy levels in an atom or a molecule are quantized, we could imagine them sitting, let's not have one at 0, we can imagine them sitting in here. like that. Those would be the energy levels inside our molecule. But that's not a very realistic case, because if we take something like a spring, but maybe a bit more realistically like an elastic band, and we stretch it, it's not perfectly Hooke's law. So this is our Hooke's law region. If we take the spring and stretch it further, I don't want to do that because I think this is a piece of jewelry or something. If we stretch it further, it will stretch and not come back. Likewise, if we stretch our elastic band, it doesn't give us all of the energy back. And so we can draw that like this, where the energy gets more open as it opens out. And that makes logical sense for our bond here. This is our bond, because the electrons in between belong to, well, they're shared between the two atoms, but if we pull them too far apart, then they can't sit right in the middle between the two atoms. They will jump to one or the other and belong to one of them, and then there'll be two separate atoms effectively and not interact very much. Then we can imagine that as we go further and further away, they will sort of lose contact with each other, and that's this curve here. Because it's flat, it means that there's no benefit in force or energy. Let's change that to energy. In force or energy, there's no benefit to the two atoms to coming closer together until they get close enough to feel each other, and then there's this little slope where they can fall down and go to the bottom of the potential well. That is the way on this diagram why the two atoms in that case are hanging around together. Okay, so that's dealt with the extension side. Let's call this how it normally is. In atoms r, the radius, the distance between the two atoms in my bond. Let's have just carbon monoxide, so there are only two atoms in it, like that. So it's the distance between the two atoms, and as we get further away, the interaction gets less and less. But let's think again about a normal spring. If we crush it down past the point where it stops being Hooke's law again, and there we would expect to be then suddenly crushing metal once these spring coils sit on each other. We're effectively trying to crush the metal and pop it over each other, maybe even distort the metal itself, and so we would expect this side to be steeper. And in the case of our molecule, whoops, I've broken my molecule. In the case of our molecule, when our atoms get close enough together, we're then trying to push the electrons into less and less space, and then we're trying to make the nuclei crush into each other and become effectively neutron star material. And that's obviously way more difficult than it would be to pull them apart. And so this side is actually steeper than a typical Hooke's law diagram. So we've distorted it now to make it more realistic. Let's put our levels in. So now the levels, because this gap is getting wider and wider faster, the levels get closer together as we get out of this mouth. So let's draw them getting closer together. And those are, whoops, they're supposed to be flat, but those are our energy levels in here. Remembering that these are vibrational levels, because it's an atom vibrating, a molecule, sorry, atoms can't vibrate, it's a molecule vibrating. It's this process in this case, whoops, sorry, it's this process. We can have our molecule at this level, and we can promote it, so we have to put a dot because it's not an electron. We can promote it up to here, the first excited state, so this would be the 0 energy level, this would be 1, this would be 2, this would be 3. Now we can excite it to different vibrational states, and because it's quantized, it can only be in these states. Okay, so now we need another little thing. here is our carbon, here is our oxygen in carbon monoxide. Let's have carbon monoxide again. So in carbon monoxide, this is the gap between them. We can push them closer together. I've drawn it too far apart, but we can push them closer together. We can pull them further apart. And at their lowest energy state that I've drawn, this is the furthest apart that the carbon and the oxygen are, and this is the closest together that they are. Now we can think about what happens when we try to excite it to another energy state. So let's try and go up to this one. If we go up to this energy state, the molecule is oscillating between here and here, and it can fall back down to its original state. So looking at this, we can imagine that this molecule, if we take the molecule and stretch it as far as it will go in its excited state, it's doing this, it can't suddenly relax to the less excited state at this distance, because the atom, in this case I'm holding on to the carbon atom, the oxygen atom can't just teleport to a different length, and there's no mechanism for it to suddenly jump there. Whoops, I'm trying to use my mouse on the whiteboard now. So if we look at that, we can see that the this molecule can only relax in this region. Outside this region, it can't possibly relax down to the ground state anyway. Here it can go down to one of the other states, but it can't relax directly to the ground state unless it's within this band here, which is a length that it would have in the ground state. This is known as the Franck-Condon principle, which basically states that the speed of a transition when the light comes in or when it goes out is so fast that the atoms can't move to adjust to it. It's also used in simulation and is called the Born-Oppenheimer Approximation, which allows you to say that the energies of the atoms, or the motion of the atoms, the motion of electrons and the motion of vibrations, can be considered separately because they happen very fast compared to each other. So you take effectively a snapshot where the atom is, and you can say where the molecule is, where all of the particles are, the fundamental particles inside there, where they are. We apply some light or allow some light to come out, and we can say those aren't going to move. So while we're on the subject of how strong, or how the probability of absorbing a light photon, that's effectively how colored a molecule is in infrared. Let us think about how that theme, because there is another quantum mechanical principle at play here. If we take a molecule such as this, which would be chlorine, something like that. If we take chlorine, both molecules are chlorine, so it's a completely covalent bond. It has no charge. And there's a selection rule. There's a rule for infrared which says that infrared bands are much more likely. Their absorption intensity is way higher if during the transition the dipole moment of the molecule is changed. So if we take the chlorine and we have a transition that makes it vibrate, so effectively it's vibrating, but it gets longer. Ooh, I should have left my drawing up. So let's do that. So if we have a transition, the average size gets longer, because although the molecule is getting shorter than it was before, and also longer than it was before because it's not symmetrical, this curve, the average size gets slightly bigger. I've drawn my averages not quite right. The average size gets slightly bigger, and therefore the molecule, to change it for another simple example, to hydrogen, this is hydrogen chloride. As this gets longer, its dipole moment, the charge distribution in the molecule, gets bigger, its dipole moment gets higher, and therefore that's a very strong transition in infrared. If we look at water, water is, oops, I've lost an oxygen off my water, must have stolen it for something else. If we look at water, water is an incredibly good infrared absorber because it has a dipole moment and it's bent, so that if one of these hydrogens gets further away because it's stretching, that will increase the dipole moment in this direction. If the other one changes, it will change the dipole moment in the other direction. If they flex like this, that will also increase the dipole moment or decrease it, depending on whether they spend more time flatter or more time straighter. And so water has a lot of active infrared transitions, and water is very effective at absorbing infrared. If we take methane, and if we make all of the bonds get longer, that doesn't change the dipole moment of this molecule, because all it does is it changes its size. It's symmetrical, it's getting bigger. Actually, carbon dioxide is a good example for that. I struggle, oh, there it is. So here's my model of carbon dioxide. Carbon dioxide has strong infrared transitions, but it also has some that are not very good. If these two oxygens get further away at the same time, so the transition is the two oxygens, the two bonds are getting longer. Ooh, it's really hard to get in play. The two bonds are getting longer and the carbon is in the middle. That doesn't change the dipole moment because both of the individual dipoles get bigger. Carbon dioxide has no dipole moment because the negative charge on both ends counteract each other effectively. So if we just make that bigger in both directions, that's just making a bigger zero, and so that has no effect. It's not a very strongly absorbing infrared band. If we move the carbon across, however, so if we hold the two oxygens still and we move the carbon in between, that's an alternative transition, and that would be infrared active. Like dichloromethane, we can see that these bonds are polar and the carbon-hydrogen bonds are not as much polar, so these are have a slight charge distribution, but the carbon-chlorine bonds are strongly polarized, so the chlorine is quite negative, the carbon is quite positive, and we can see that this molecule, if we sit it like this, has a slight negative charge on this end and a slight positive charge here somewhere. That will cause it to be relatively infrared active, so that if this bond or these two bonds increase in their stretching, because we're thinking mostly about stretching, it will that will be infrared active because it will change the dipole moment of the molecule. It will make it stronger. If we flex this one, that will also change the dipole moment. If we flex this one, it won't change it very much. So now I've written it down because this is an important point. There is a selection rule for infrared, a quantum mechanical selection rule, that states, or that we discover, that the dipole of the molecule should change for an infrared transition to be very strong. It's a selection rule, so it's quantum mechanical rule, but because it's quantum mechanics, it can break it. So if the dipole moment doesn't change, it doesn't mean that we don't see the transition at all. It means that it's comparatively weak. Because in quantum mechanics, things just get less and less likely, they don't really become impossible. We can, however, use this to our advantage, that quantum mechanics doesn't fully disallow anything. So if we take a light beam and we excite our molecule with a lot of energy, we can excite it up to here, and there isn't actually a quantum mechanical state here, so it has to fall back immediately. Go back immediately back down to the ground state. We can draw it going back down again, and it gives back out the light. We see that as scattering. So if we look in the sky, why is the sky blue? It's blue because light scatters off molecules. It goes into the molecule, and the molecule has nowhere that it can absorb it to, so it spits it immediately back out again. However, quantum mechanics is not 100%, so there is a small but non-zero possibility that it, instead of going back down into the state that it came from, it goes into a different energy state. So let's have it going up to here with one arm. No, it's not an electron, with two arrows. So let's have it going up to this virtual state that doesn't really exist. It just goes up to an energy amount, but there isn't a quantum mechanical state for it to sit in, so it has to fall immediately back down again. But it can fall into a different vibrational state as long as the atoms in the molecule, the nuclear distances, don't have to change for it to get into that state. As you can see, we've done exactly the same thing as we did before. So the infrared transition would be this. We shine infrared light on it and it goes up one vibrational level. And this other transition goes up to some magic level and then comes back down again. So it goes up to a non-existent virtual level and it comes back down again, and it's also gone in sum exactly the same. So we've done an infrared, but we've done it in a different way. And that is really handy because it means that we have a different selection rule. This type of spectroscopy is called Raman or Raman spectroscopy. Apologies to Indian people. It's an Indian name and I can't pronounce it. So Raman spectroscopy. And the selection rule for this is not that the dipole moment has to change, it's that the polarizability changes. That means that this transition that we were speaking about before, where all of the hydrogens in a methane get further away because they're all excited at the same time, all of these bonds, all of these vibrational states are all excited, the molecule effectively gets bigger. Because the electrons are further away in this excited state, the polarizability of the molecule, the ability of an external field to push the electrons around effectively, goes up, and that makes that a Raman active state. Why is this important to us? Well, my course students are biomaterials students, and biomaterials are typically wet, so they're proteins, sugars, some kind of other things in water. This is water. Whoops, shouldn't hold it by the oxygen. This is water, and water has a lot of infrared active transitions. However, most of them are not Raman active. What this means in practical terms is that we can measure a Raman spectrum of our molecule in water far more effectively than we can measure an infrared spectrum in water, because water is very, very absorbing in infrared and gets in the way of nearly every measurement that we want to make. If we want to make an infrared measurement, we typically try to make things as dry as possible. The probability of Raman scattering, where the energy comes out differently, is very low, as we just said, because it's quantum mechanically not allowed. It's very low, and therefore we need a lot of light to do it. So typically we would have a laser coming in and causing this transition because it's a very bright source and it's one color. Because if we had a different color, if we use just a normal light source, we would have this line would be a different length, so we could excite it to a different level, and then we would get this light out, but we wouldn't know, we wouldn't be able to measure it. What we're physically trying to do is put in this light, get this light out, and measure the difference in color between the two. But the probability is of the between 1 in 10 to the 9 and 1 in 10 to the 12, so most of the photons will be scattered, so they will go straight back down, and we get a very bright light of the color that we put in. So we need to get rid of that practically if we want to do this measurement. So we need a type of filter that cuts out one color very effectively, and we want to measure comparatively close to it because we've got an infrared transition. It's not very much energy, and very often in practice this is a red or green laser, so that it has a narrow color and a very high intensity, so that we can measure this very low probability event.